And here is part of the planning graph for the simple DocWorker Robux example you've seen earlier. You remember the initial state consisted of 6 proposition symbols, and in our proposition layer P0 we find nodes for these 6 symbols. So each of these proposition symbols represents a node in our graph, which means we have 6 nodes. And the blue background is simply to indicate the layer as a whole. So this is proposition layer P0. And with this proposition layer fully defined, we can see which nodes are in the following action layer. And these are only those action symbols that would be applicable in this state. Again, these are 4 individual nodes here, all together making up the action layer A1. And before we look at the next proposition layer, we can introduce those edges that connect these actions to their preconditions, and they are shown here as black lines. Now, given our proposition layer P0 and our action layer A1, we can define our proposition layer P1, which contains all the nodes from P0 plus all the positive effects of actions in A1. And these are all those propositions we see here. Again, these are individual nodes, even if they're not shown as such. The blue background indicates what constitutes this proposition layer, and that is all that is in proposition layer P1. And we need to connect this layer to the preceding action layer, on the one hand through the positive effects of the actions, so these are the green lines here, and then we also have the negative effects that are indicated as red lines here. And this is the planning graph up to and including proposition layer P1. And we can now continue with the action layer A2. Now we take proposition layer P1 and interpret it as a state, and see which actions would be applicable in that state. And that's this list here. That's all the actions that are in action layer A2. And again, we have to introduce edges or arcs from P1 to A2, representing all the preconditions of these actions. And they are given here. And with P1 and A2 defined, we can now see which nodes are in proposition layer 2, P2. And these are given here. Again, they're individual nodes rather than just one set. But that is the whole set of nodes in proposition layer P2. They are all the nodes from P1 plus the positive effects of actions in A2. What's missing are, of course, still the edges, and we need edges that connect propositions in P2 to actions where they are positive and negative effects. And again, we have green lines for positive effects and red lines for negative effects here. And so on. Here come the propositions that are in action layer A3. And they are connected through edges to their preconditions. And we will do one more. Here come the propositions in proposition layer P3. And again, we have to have edges that connect them to actions where they are positive or negative effects. And of course, I could be continuing with this graph here, but A, I'm running out of space, and B, I think you get the point now. Earlier, I talked about reachability of goals and reachability of individual propositions in a goal. Now we will look at the planning graph and see what the planning graph can tell us about reachability. So here is what we can say about the planning graph. Suppose we're given a planning problem and construct the planning graph for this problem. Then we have the following. If a goal G is reachable from the initial state Si, then there must be a proposition layer PG in our planning graph such that all the goal conditions, all the nodes representing those propositions that are goals, are a subset of this proposition layer PG. The proof of this is very simple, as you can see. If the goal G is reachable from Si, then there must be a plan, which is an action sequence that achieves this goal. And if we construct a planning graph consisting of 2n plus 1 layers, where n is the length of our solution plan, then this plan is contained in this planning graph, where we select the first action in the first action layer, and so on. And that must achieve the goal. So that means in our last proposition layer, all the goal proposition must be contained. One caveat here is that this only works in one direction. So if we have the first part true, then we can conclude that there must be such a layer in the planning graph. So you can look at it the other way around. If there's a goal condition G that is not contained in our final planning graph layer PG, then this goal condition can't be achieved within this planning graph. And that, of course, means that the overall goal can't be achieved in the planning graph. So what this gives us is a necessary condition for when a solution must exist, but not a sufficient condition. So we can compare this to the reachability tree we have looked at earlier. The reachability tree was a sufficient condition for testing whether a goal state exists. And that is because all the nodes contained sets of propositions that must necessarily hold in that state, and all the propositions in those states were consistent. Whereas the planning graph contains propositions in these proposition layers that may hold, but whether they hold or not depends on the actions we select in the previous action layer. Also, the proposition layers quickly contain sets of inconsistent propositions. That means propositions that can never be true in the same state. As we've seen, a robot can never be at location 1 and location 2 at the same time. Similarly, the actions in one action layer may never be applicable at the same time. So there were actions for moving a robot from one location to another and back in the same action layer. Those two actions can, of course, never occur in parallel. So the planning graph only gives us a necessary condition for goal existence. We can look at the last proposition layer, and if our goal is not contained in the last proposition layer, then this planning graph does not contain a solution plan. The big advantage of the planning graph is, of course, the low complexity. The planning graph is polynomial in size, and it can be computed in polynomial time. And this can be seen quite easily because each action layer and each proposition layer can contain at most all the propositions we have, and that is a finite number. And we have n layers in our graph, so we can have n times the number of symbols we have, and that is polynomial. In other words, we have a criterion for plan existence that we can evaluate in polynomial time, but unfortunately, it's only a necessary condition.